I want you to picture a scenario. It's a Tuesday morning, about 10:00 a.m.
Okay.
The coffee's just kicking in and the shop floor is doing its thing. You hear that high-pitched whine, the one of a spindle, running at like 20,000 RPM, just shredding through 663 aluminum. It's a good sound.
Oh, yeah. It sounds like money. It's the sound of a happy aluminum profile machining center.
Exactly. It's your workhorse. It's fast, it's agile, it's making window frames or whatever. But then the door opens. A longtime client walks in, drops a drawing on the desk, and says, I need 10 of these by Friday.
Right.
You look at the print. It's not aluminum. It's a fixture plate. And the material spec is #45 steel, or maybe something even nastier, like die steel.
And the room goes quiet.
The room goes dead quiet.
Yep.
Because you look at your machine,
Right.
your sprinter, and then you look at that block of steel, the linebacker, and you get that pit in your stomach.
Mm-hmm.
You're thinking, if I put that steel in my aluminum rig, am I going to blow up my spindle? Is the gantry going to twist? Do I have to turn this job down?
It's the classic job shop dilemma.
Yeah.
Do you stay in your lane, or do you risk your equipment to solve your client's problem?
So that is our mission today. We are digging into a stack of technical manuals, some user reports, to answer one simple question. Can an aluminum profile machining center actually cut steel without destroying itself?
And the short answer? Yes.
Yeah.
It absolutely can. But, and I cannot stress this but enough, you cannot just load the steel and press go.
Right.
If you treat steel like aluminum, you will destroy your tooling, and you might actually damage the machine.
So the machine is capable, but the operator needs a brain transplant.
A mindset shift, let's say.
Mm-hmm.
You have to pivot from a philosophy of high efficiency, which is, the aluminum game, to a philosophy of rigidity and thermal management.
You're trading time for capability.
That's the perfect way to put it. You're trading time for capability.
Okay, let's unpack that trade-off. Because in this business, time is money. If I have to run the machine at a snail's pace, does the math even work out? And maybe more importantly, why does the physics change so drastically? I mean, metal is metal, right? Steel is just harder.
It's so much more than just harder. The physics of the cut are, fundamentally opposed.
Yeah.
To understand why we have to change everything, the tool, the coolant, the speed, we have to look at what's happening right where the tool meets the metal.
Okay.
When you're cutting aluminum, what's the goal?
Speed. Get the material out of the way as fast as possible. It's gummy. It wants to stick to everything.
Right. It's soft and sticky. It wants to weld itself to the cutting edge. So the strategy is high surface speed. You spin that cutter crazy fast to shear the material off and get that chip out of there instantly.
You want the heat to leave with the chip.
Exactly. You're relying on the chip to carry the heat away. Aluminum is a fantastic thermal conductor. The heat transfers into the chip flies away. It's almost a self-cooling system.
It's that snowstorm effect. If the chips are flying, the heat is flying.
Perfect. Now, swap in a block of #45 steel.
The steel is not a great conductor.
It's basically an insulator by comparison.
Yeah.
And it has extremely high shear strength. So you aren't scooping material anymore. You are tearing through a structure that does not want to move.
And that generates friction.
Massive friction. And friction equals heat. Intense heat. If you run at aluminum speeds, thousands and thousands of RPM, you are generating heat way faster than the material can release it. The heat doesn't go into the chip. It stays right there in the cut zone.
How hot are we talking?
You can spike the temperature to over 1,000 degrees Celsius in a fraction of a second.
Whoa, so the tool just cooks.
It cooks. It anneals itself. And because an aluminum profile center is generally lighter, it lacks the sheer mass of a big cast iron steel mill. All that energy creates vibration. So now you have heat softening the tool and vibration just shattering the edge. It's a catastrophe.
Okay, so speed kills. The obvious solution is slow down. But here's where I get skeptical. If I slow my RPM way down, don't I lose all my torque? These high-speed spindles, they're not designed to grunt through material at 500 RPM. They'll just stall.
That is a very, very real risk. You can't just drop to 300 RPM like you're on an old Bridgeport. You have to find that sweet spot in your spindle's torque curve.
And then adjust the feed rate to match.
Right. That's the chip load calculation. It's the thickness of the slice each tooth takes. If you slow the RPM but keep the feed rate high, the chip load gets huge and you'll stall the spindle or just snap the tool clean off.
But, and I think I know the answer here, if you go too slow on the feed,
You're not cutting anymore. You're rubbing.
you're just polishing it.
You're rubbing, and rubbing causes work hardening. You actually make the surface of the steel harder by compressing it, which then, of course, destroys the tool even faster.
So it's a tightrope. You have to be slow enough to manage the heat, but aggressive enough to actually form a chip so you don't just glaze the material over.
Precisely. It's like you said, you are driving a Ferrari like a tractor. You need to find the gear that gives you traction without burning out the clutch.
Let's talk about the tires on that tractor then, the tooling, because the research made this really bold claim. Using an aluminum end mill on steel is like trying to cut a steak with a plastic spoon.
It's a perfect analogy. It really is.
But visually, aluminum tools look sharper, you know? They have those deep valleys, really aggressive rake angles. Why is sharp a bad thing for steel?
It all comes down to structural integrity. Look at an end mill for aluminum. It usually has 2, maybe 3 flutes.
Right.
To make those big, deep valleys, the gullets, so the big, sticky aluminum chips can escape, you have to remove a lot of the tool's body. The solid cylinder of carbide in the center, what we call the core diameter, is actually pretty thin.
Which means it's flexible, it can bend.
In aluminum, that's fine. The cutting forces are low. But in steel, the forces are massive. If you use that thin core tool, it will deflect. It will bend. And then it will snap.
So for steel, we need a thicker core, more beef.
Exactly. For steel, you want 4, 5, or even 6 flutes. More flutes means smaller valleys, which is okay because steel chips are smaller, but it allows for a much, much thicker and more rigid core. It's all about beam strength.
And the sharpness part.
A razor edge is fragile. If you drive a razor edge into hard steel, it just chips away instantly. So steel tools use a more negative rake angle. They're less like a knife and more like a wedge. They push the material apart rather than slicing it. It's more of a brute force geometry.
Okay, that makes sense. Now I want to get into coatings, because this was the part of the research that honestly kind of blew my mind a little bit. I usually see aluminum tools that are just polished carbide.
Yeah.
They're shiny. But for steel, you're recommending something like tin.
Titanium aluminum nitride, the dark gray or sort of violet coating.
I always just thought coatings were to make the tool harder, like a protective shell. But you're saying it's actually a chemical reaction?
Yeah, it's fascinating chemistry. Toluene is what you could call a smart coating. When it gets hot, and remember, cutting steel gets really hot, the aluminum in that coating reacts with the oxygen in the air.
Okay.
It forms a microscopic layer of aluminum oxide.
Which is ceramic.
Exactly. It essentially grows its own ceramic heat shield right there during the cut. This shield acts as a thermal barrier and stops the heat from getting into the carbide tool itself.
Wait, so the hotter it gets, the harder it works to protect the tool?
To a point, yes.
Yeah.
It's amazing. Without that coating, the heat soaks into the carbide binder, the tool softens, and the edge just wipes away. With the coating, the heat goes into the chip, not the tool.
That is incredible. So the practical takeaway here, if you're digging through your tool bin and you grab a shiny 3-flute cutter,
Put it back.
put it back immediately.
Put it back. You need the dark, coated, high flute count cutter.
Yeah.
Otherwise, you're just throwing money in the scrap bin.
Okay, let's move to the environment inside the machine. We've established heat is the enemy. With aluminum, I'm used to just using an air blast. You know, keep the chips clear, keep the mess down. But for steel, you're saying air isn't going to cut it.
Air is absolutely not enough. And this brings us to what I call the ghost part phenomenon.
The ghost part. I think I know what this is. This is where you measure the part while it's still on the machine, and it's perfect.
Dead on.
You take it off, let it cool down, and an hour later, it's out of tolerance.
It's heartbreaking. And it happens because of thermal expansion. Steel moves a lot when it gets hot. If you are dry cutting steel on a light machine, where you're already generating excess heat because you have to move slower, the workpiece temperature just climbs and climbs. It expands.
So you're machining the expanded version of the part.
Correct. You cut it to size, then it cools down to room temperature, and it shrinks. Now your holes are too close together, or your overall length is short.
So we need flood coolant.
You need to drown it, high volume. But here's the thing that people miss to me. Coolant isn't just for cooling, especially on a lighter aluminum rig.
What else is it doing?
It's a structural aid.
Explain that. How does liquid help the structure of my machine?
Lubricity.
Yeah.
Remember, we are fighting friction. A good coolant emulsion makes that cutting zone incredibly slippery. It lowers the coefficient of friction between the tool and the steel.
Okay, so it's slippery, which makes it easier to cut.
And if it's easier to cut, it requires less force to push the tool through the material. Less cutting force means less pushback against the spindle and the gantry.
And since our gantry is light.
Exactly. Reducing the cutting force by even 20% through proper lubrication can be the difference between a smooth cut and a chattering, screaming mess. You are helping the machine punch above its weight class.
That connects perfectly to the final and probably the biggest hurdle, rigidity. You compared the machines to a tank versus a sprinter?
Yeah, a dedicated steel mill, a VMC, with a heavy cast iron base, that's a tank. It has mass. Mass dampens vibration. When the tool hits the steel hits back. Newton's third law. The tank just absorbs that hit.
And our aluminum profile center is the sprinter.
It's built for acceleration. Extruded aluminum frames, lighter gantries. When that steel hits back, the sprinter,
Yeah.
it flinches. The frame actually flexes, just microscopically.
And that flex is chatter.
It's resonance. The machine starts to vibrate at its natural frequency. That's that horrible screening noise. And the surface finish looks like a vinyl record.
So how do we stop the sprinter from flinching? We can't just make the machine heavier.
No, but we can change how we ask it to push. We have to change the math of the cut. This is where we get into depth of cut and width of cut, or AP&A.
Right. Traditional thinking for steel is go deep and slow.
On a tank, yes. You might bury the tool 10 millimeters deep and cut a wide slot, but on a light machine, that creates massive lateral force, pushing sideways against the gantry. That's its weakest direction.
So we need to change direction.
We use a technique often called high-efficiency milling or dynamic milling. The strategy is high axial depth, low radial width.
Okay, translate that for the shop floor.
You use the whole side of the flute, maybe 15 millimeters deep, but you only take a tiny little nibble of width, maybe just 5 or 10% of the cutter's diameter.
So a very tall but very thin slice.
Exactly. Think about the physics of that. By taking such a thin radial slice, you drastically reduce the side load on the tool and the gantry. You're directing the cutting force more tangentially, using the spindle's vertical stiffness, which is usually its strongest point.
You're playing to the machine's strength. You're avoiding the weak lateral push and using the strong vertical stability.
You're hacking the physics. You're tricking a light machine into behaving like a rigid one by simply never asking it to push harder sideways than it can handle.
This sounds like it requires specific cam strategies, like trochoidal milling.
Trochoidal or other dynamic tool paths are the absolute best way to do this. The tool moves in these smooth, looping paths instead of straight lines. It keeps that tool engagement constant and low. If you jam it into a corner, the engagement spikes, and that's when you'll get chatter.
But again, this brings us back to time. If I'm taking tiny 10% step overs, that's going to be a lot of passes.
It is. It is a lot of passes. But because the load is so light, you can actually increase your feed rate quite a bit, so you recover some of that time. But yes, ultimately, it will be slower than a dedicated steel mill.
But the part comes out correct.
The part comes out in tolerance, with a good surface finish, and your spindle lives to fight another day.
Okay, so let's wrap this up into a protocol. A checklist for the operator standing there with the drawing in one hand and a sense of dread in the other. Step 1.
Step 1 is mindset. Accept that you are not in a race. Quote the job with extra hours. Don't promise aluminum prices for steelwork.
Step 2. The hardware.
Strip the machine of any aluminum tools. Load up with high flute count 4 to 6 thick core, TL-encoded carbide end mills. No shiny cutters.
Step 3. The wet work.
Flood coolant, maximum pressure, maximum volume. You need that thermal stability, and you need that lubrication to lower the cutting forces and help your machine out.
And step 4. The strategy.
Low radial engagement, high axial. Don't try to slot deep. Take light, tall bites. Peel the material away rather than gouging it. Keep the forces directed in a way the machine can actually handle.
It sounds totally manageable when you break it down like that. It removes the mystery.
It's just physics. The machine doesn't know its name is aluminum profile center. It doesn't read the sticker on the side. It just reacts to force and heat. If you control the force and the heat, the machine will cut the material.
I love that. The machine doesn't read the sticker. That's empowering. It means your capabilities are defined by your knowledge, not just your equipment list.
That's the whole ballgame. A smart operator with a light machine can outperform a careless operator with a heavy one any day of the week.
So next time that client walks in with a block of die steel, don't immediately say no. Check your CAM software, check your tool crib, and see if you can trade a little bit of time for a whole new capability.
Just remember to clean the machine out thoroughly afterwards. Steel chips rust, and you do not want that messing up your nice aluminum jobs later.
That is a great point. Machine hygiene matters. Thanks for breaking down the physics for us.
My pleasure.
And for everyone listening, thanks for diving deep with us. Go check your chip loads, keep your coolant topped up, and we'll see you on the next one.